Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the reactions of carbohydrates. And as we know that carbohydrates are polyhydroxyaldehyde or the ketones, and which on hydrolysis gives the unit is known as a carbohydrate. And generally most abundant carbohydrates are pentose and the hexose, and among the hexose glucose and fructose. Glucose and fructose are both enantiomers of each other, and in aldohexose, the IUPAC name of that glucose is aldohexose, and whereas fructose is that is as a ketohexose. That are the IUPAC name of that compound. And yesterday we have learned some of the collective reaction of the glucose molecule, D plus glucose molecule, and that glucose molecule or the generally whatever carbohydrate chemistry, whatever organic compounds are there, carbohydrate compounds are represented according to as a Fisher projection formula. Fisher projection formula used to represent the carbohydrate chemistry or the carbohydrate compounds. And mostly as a glucose we are studying the reaction of glucose, properties of the glucose, structure of the glucose, everything we are learning simultaneously under the heading is the basics of carbohydrates. In that basics, and also we have learned D and L configuration. Remember, D and L configuration means what? That in the beginning or the yesterday we have seen how the DL configurations are assigned over there. Do you know the optical rotation is an experimental measurable property of a compound? Configuration of chiral carbon to observe by simple experiment in 1951. X-ray crystallography studies of plus sodium rubidium tartarate established its configuration as C double bond O minus, then OH on the right hand side, another OH on the left hand side, and COH. That is and this was the first instance of the determining absolute configuration. And as we know that D and L configuration, whereas R and S are called as a absolute configuration, and a monosaccharide is assigned DL configuration on the basis of the configuration of the lowest chiral carbon in its Fisher projection formula. And now we have learned with the help of figure we have illustrate how the D configuration of plus glucose is assigned, and reference compound is taken as a D plus glyceraldehyde. Why D? Because OH or the lowest chiral carbon in its Fisher projection, if you observe those structure, you will find that the hydroxy groups are present on the right hand side, and that's why it is designated or it is assigned as a D configuration. And suppose that lowest chiral carbon, if it is present on the right hand side, then we can call it as a what we can call it as a L configuration. That are the relative configuration we have seen, and generally the absolute configuration the absolute configuration is assigned on the basis of RRS configuration. And we know that in the glucose there are 4 chiral centers are there, according to as a forms of rule 2 raised to n is equal to number of isomer is obtained. Suppose as there are 4 chiral center, if you put the value of n in above formula 2 raised to 4 is equal to, that becomes 2 into 2 into 2 into 2 is equal to 16. There are 16 stereoisomers are possible, or the 8 pairs of enantiomers are obtained, and so that type of the thing we are generally talking about, or we have discussed about. And today we are going to discuss the next point, oxidation, that is the effect of alkali. Oxidation we are going to talk today. Oxidation, that is effect of alkali, that is a reaction of glucose. Effects of alkali, which is known as the reactions of glucose. And now under this aldohexose can be oxidized in 4 important ways. Aldose means where it is containing as a aldehyde group, and therefore the according to as a IUPAC nomenclature system we can call it as aldose, means there are aldehyde group is present in that compound. Then aldoses can be oxidized in 4 important ways by number one is a failing or Toulin's reagent. And reagent, we know that in while studying as a retrosynthetic analysis, where we have seen as a definition of the reagent. Reagent means what? They are the compound which react to give an intermediate, or target molecule itself is known as a reagent. So that is the simplest, or whenever we are adding the compound where the changes are occur, that type of the thing is called as a reagent. Failing or Toulin's reagent, we are talking about the effect of the alkali, means reaction of the glucose. Here we are talking. So first one, by failing or Toulin's reagent, that is oxidation by, these are the oxidation by mild oxidizing reagent. Oxidation by mild oxidizing agent. We know that a mild oxidizing agent, and it is oxidized to gluconic acid. And when you are using as a mild oxidizing reagent, and it is oxidized to gluconic acid, it is oxidized to gluconic acid, as we know that gluconic acid. And one, we know that one, the simplest, while studying as a reaction of the glucose, we generally representing the simplest form of glucose. How we are writing that? CHO aldehyde group, which we are writing at the top, and then collectively CHOH, and that 4 times, and then we are writing CH2OH. This is the general representation of the glucose while writing its reaction, that you have to remember. Here this is the structure of glucose over here, plus glucose you can call it as a, and here OAC indicate as a sugar unit. Now when this is treated with, yesterday we have already seen this one, Br2 in presence of water, H2O, and as we know that it is a mild oxidizing reagent. Remember why it is a mild oxidizing reagent. What the mild oxidizing reagent do? That mild oxidizing reagent oxidize the carboxylic group, and which we are getting over here COH, then CHOH here 4 times, and finally this is CH2OH, and this reaction the compound which we obtain is known as gluconic acid. This is known as a gluconic acid, or other way around, the name of this compound is a gluconic acid, right? And that we have got over here. Even by mild oxidizing reagent, we got this gluconic acid. And suppose instead of this failing solution as well as Toulin's reagent, they are also known as, or they are also used as a mild oxidizing reagent. Failing solution as well as Toulin reagent also used as a mild oxidizing reagent. So what is going to happen over here? Let us see how the reaction takes place when you perform the reaction of glucose with failing solution or the Toulin's reagent. First of all, let us see first one is a CHO. As we know that here CHOH 4 times and this CH2OH. Generally we are writing this is the shortest, easiest form of the glucose we are writing for the reaction point of view or reaction purpose, that you remember here. Here is this is the structure of glucose, right? And that glucose when treated with the Toulin's reagent, do you know the Toulin's reagent will be twice Ag, then NH3 twice OH. This is the formula of Toulin's reagent. This is the formula for, this is a Toulin's reagent. Toulin's reagent, right? And this Toulin's reagent, it is a mild oxidizing reagent. Similar, it is a mild oxidizing reagent. It is a mild oxidizing reagent, and this mild oxidizing reagent, when heated, this triangle indicates as a heating. When it is heating, the oxidation takes place over there, and when the oxidation takes place, what is going to happen? This aldehyde group is converted into as a carboxylic group, and as we know that C double bond OH, then here CHOH, this 4 times, and this CH2 and OH, it is remains as it is, and this the compound which we got is nothing but as a gluconic acid. As we know that this is a gluconic acid, or which we previously known as a monocarboxylic acid. This is known as a, when monosaccharide acid, from that we are getting this, these are nothing but as a monosaccharide, and monosaccharides, or we can call it as a monocarboxylic acid. Monocarboxylic acid. This is a speciality of that mild oxidizing reagent. They only oxidize the aldehyde group into carboxylic group, and which is known as monocarboxylic acid. So this is there. Now when you treat this compound, this glucose with the another, let us see here, we are writing here CHO, then CHOH 4 times, and then CH2OH. When it is treated with twice Cu plus means that is a what we can call it as a failing solution. As we know that the failing solution plus 5NaOH, right? Copper and plus 5NaOH. This is known as a failing solution. This is known as a failing solution, or which this failing solution first time discovered by the scientist. The name of that scientist is Benedict. I think that is a Benedict solution. Also it is known as Benedict solution. And what does it do? Benedict solution or the failing solution, what does it do? It will convert this aldehyde group which is present in the glucose, that is going to convert into as a carboxylic group. And here just hitting it, that oxidation reaction takes place and it will produce this one. That's you remember C double bond OH. Then here as it is CH-OH is a 4 type, and this one is a CH2OH. Primary remains as it is, and this is again nothing but as a gluconic acid. This is the product which we are getting over here. So in this way we have seen there are 3 oxidizing reagent, mild oxidizing reagent. All are this is known as a alkali effect. Alkali means in everywhere there is a alkaline solution, and therefore they are the mild oxidizing reagent. They oxidize the aldehyde group into as a carboxylic group, means we are getting as a monocarboxylic acid. And from these 3 reaction we can infer that the glucose containing one aldehyde group or one fermyl group. This was the what we can call it as a observation we can draw from this reagent. And all these 3 are the mild oxidizing reagent which they convert the carboxylic group into as a. Then second reaction will be by bromine water, which we have seen. And then next one is the nitric acid. As we know that nitric acid generally we are encountered with that dilute nitric acid, the reaction, and what is happening, that gives the saccharic acid or gluconic acid. Saccharic acid, that gives as a saccharic acid or gluceric acid. So remember, as a saccharic acid means it is a dicarboxylic acid, means there are 2 carboxylic groups are present when the glucose is treated with the dilute HNO3. What is happening there? The aldehyde group which is converted into as a carboxylic group, as well as the primary alcohol present at the bottom when we are writing the glucose according to as a Fischer projection formula. This is a general way of representing glucose on a blackboard. So that primary alcohol also get oxidized into as a carboxylic group, and therefore a resulting compound will be the dicarboxylic acid. And that dicarboxylic acid, the name of that dicarboxylic acid is a saccharic acid. Remember this one. And so in the first place they cannot be used to differentiate aldoses from ketones. And whatever reaction we have performed, we have seen. So in aldose and the ketose, as we know that aldose means containing as a fermyl group, ketose containing as a ketone group, C double bond O, ketonic group, and here is a aldehyde group. In the first place they cannot be used to differentiate aldoses from ketones in the first time. So remember, in the first place they cannot be used to differentiate. They cannot be used to differentiate aldoses from ketoses. And ketoses to reduce filling solution and Toulin's reagent, and this behavior is a characteristic of alpha hydroxyketones. Remember here, aldose as well as ketose, aldose containing aldehyde group, whereas ketose containing as a ketonic group. and when these two are treated with ketones as well as aldones, both are get reacting, giving the same product. So in the first place we cannot use to differentiate aldoses from ketoses. So that is the this is the behavior, is the characteristic of alpha hydroxy ketones. Okay, and in the second place, oxidation by Fehling or Toulin's reagent cannot be used for the preparation of aldonic acid, monocarboxylic acid. Aldonic acid, that is a monocarboxylic acid from aldoses, both Fehling's and Toulin's reagent are alkaline reagent. Remember here, both are containing as a alkali there, sodium hydroxide, and here also as a hydroxy groups are there, and therefore both the are alkalis present here, present reagents, and the treatment of sugars with alkali can cause extensive isomerization and even decomposition of the chain. And alkali exerts this effect. This Toulin's reagent as well as Fehling solution, they exerts these alkali effects in part at least by establishing an equilibrium between monosaccharide and an enediol structures. And what does it mean, alkali effect or the enediol structure? Let us see over here. I am just cleaning this. I am trying to explain the oxidation or effect of alkali, that are the reactions of the glucose which we are learning, which we are discussing here. Let's see what is going to happen over there. Here the enediol sorry, what do you mean by the enediol? E and E indicate as there are the carbon-carbon double bond, as we know that the general structure of that. Here we are writing H, and here one more carbon atom I am representing here, hydrogen, and then this is a aldose. We can remember this is a aldose, and that aldose at an equilibrium, what is going to happen at an equilibrium? This is formed as a enol form of that compound. Then that hydrogen goes over there. So COH, then double bond CH and OH. Here we can write COH and this CH as it is, and this zigzag line indicate that the rest of the part over there. So this is this is enediol. This is called as a enediol. Enediol means there are carbon-carbon double bond. ENE suffix indicate as a carbon-carbon double bond over there, and this is happening. This is attaining at an equilibrium, and this type of the carbon-carbon double bond and OH adjacent to OH, and now that goes again at an equilibrium, so that can form as a this type of the compound. Again aldose will get, see here, HO, H, then CHO, this, and then C, H, and HO we can, or this OH we can write this OH, as well as you can take this mannose type of the compound, and this is a aldose type of the compound. Both are the aldose, and they produce as a enediol. So both hydroxy group, that is a mannose type of the compound, is the aldose, and this also has aldose, but remember both are giving at an equilibrium is a enediol. How this equilibrium is attained, that see that look here very carefully, and you will observe over here, this is a enediol we are getting over there, and that enediol can further be at an equilibrium. This we can convert into if OH. So here you will get this one CH2OH. Only there is a distribution of hydrogen atom. Only small atom, hydrogen atom can distribute like this, OH and EH. We can write this one, that is nothing but as a, this is a ketose, right? This is a ketose over there, ketose. This will be the ketose, CH2OH, C double bond. This is a ketose form, and this ketose form can be at an equilibrium is converted into this type of the enediol. Now this is going over there, so this CH2OH we can write over there, then here COH double bond, then CHOH, and this one we can write as it is. So this will be the again as a we go on showing this one etc. This type of the enediol we will get over here, enediol like this. So this is enediol, this is also enediol, which is this one is obtained from an aldose, and this will be obtained from the ketose. Means both are giving at an equilibrium is converted into as a enediol. So this is something about that enediol. Let us look at as a second one is a bromine water, which we already discussed that. So bromine water, it is a mild oxidizing reagent which will oxidize the glucose into as a gluconic acid. Oxidizes aldoses but not ketoses. Remember, this Br2 in presence of water, it will oxidize which one? Only as a this one. As we know that aldose and the ketose, if you treat with the Br2 in presence of H2SO4, what do you get over here? So here you are going to get this type of the compound. As we know that there are two structures are there. One is a glucose, we know that here CHO, then CHOH 4 times, and then CH2OH. This is the structure of glucose. Another structure CH2OH, then C double bond O, then CHOH 4 times, and this CH2OH. This is the structure of fructose, right? This is the structure of fructose. When it is treated with Br2 in presence of H2O, what does it gives? And when it is treated with Br2 in presence of water, what it gives, or what type of the product is formed. And as we know that this is a mild oxidizing reagent, mild oxidizing agent, right? And what it will do, it will convert that aldehyde group into as a carboxylic group like this, CHOH 4 times, and there CH2OH. But in this case, look at here, there is no aldehyde group. Here primary alcohol, here also as a primary alcohol, ketone is already oxidized. This is a mild oxidizing reagent. It won't get, means there will be no reaction over here. No reaction will take place over. That's the inferred we can draw from this. Oxidizes aldoses but not ketoses. As an acidic reagent, it does not cause isomerization of the molecule, and it can therefore be used to differentiate an aldose from ketose, and is the reagent chosen to synthesize the aldonic acid, monocarboxylic acid from an aldose. Remember, this is one of the best tests to get that carboxylic acid into as a, what we can call it, into as a gluconic acid here. So it will not oxidize the fructose, there will be a no reaction. But now remember, when this glucose is treated with, suppose this is a starting compound, as we know that it is a glucose, when it is further treated with these reagents, two reagents, suppose here is a Br2 in presence of water H2O, and here is a dilute HNO3. What type of the product they produce, or what would be the product obtained here? Let's see how we can get the product over here. Look at here, this is a mild oxidizing reagent. We know that it gives COH, then CHOH 4 times, and then CH2OH, that is a gluconic acid. This one is a gluconic acid, or it is known as aldonic acid. Aldonic acid, which is known as a gluconic acid or aldonic acid, that are the name. Now when dilute HNO3 nitric acid is treated with that glucose, starting compound is a glucose, the resulting compound obtained, what is happening there? This is a mild oxidizing reagent. It is a mild oxidizing reagent, whereas it is a strong oxidizing reagent. These are the opposite or synonym word. So not synonym, what we can call it, opposite word. One is a mild oxidizing reagent, another one is a strong oxidizing reagent. Remember, strong oxidizing reagent also oxidize primary alcohol into as a carboxylic group. And so what you are going to get? COOH, then CHOH, there is a 4 time, and another one also COOH, and this is the structure which we got, that is also called as a saccharic acid. Saccharic acid, this one is called as a saccharic acid, or it is a dicarboxylic acid. Look at here, C double bond OH and C double bond OH, 2 carboxylic groups are there, and therefore it is a what we can call aldonic acid, or what we can call it as a saccharic acid. Aldonic acid, this is called as aldone, not this one. Please make the correction over here. This is known as a gluconic acid, and this is known as a aldonic acid or the saccharic acid. Aldonic acid or the saccharic acid, better way to remember as a saccharic acid. This is the easiest way to avoid the confusion between as a gluconic acid means monocarboxylic acid and saccharic acid means dicarboxylic acid. So or aldonic acid is nothing but as a dicarboxylic acid. So this way we got this one, then a strong oxidizing reagent which we have just now, then oxidation by HiO4 per iodic acid. HiO4 is used as an oxidizing reagent. How it will cleave the carbon-carbon single bond between as a 2 adjacent carboxylic acid hydroxyl group, or maybe as a carbonyl and the hydroxyl group, but the condition for it, they must have 1-2 position, then and then reactions are occur. So then reduction reaction, I think that reduction reaction we will see in the next lecture. Today let us stop today here. Thank you, have a nice day.